new components called mixers, which are used for frequency translation. I've drawn mixers in their two common configurations in the upper left. There are 3 ports on a mixer, usually labeled RF, IF, and LO. These stand for radio frequency, intermediate frequency, and local oscillator. Regardless of whether RF is the input and IF is the output, or IF is the input and RF is the output, the mixer does the same thing, which is multiply the input signal by LO. To do this, the mixer generally relies on LO being a very large signal. This multiplication has the effect of moving frequencies in the input signal to a different place, which is the primary purpose of the mixer. Here's an example of how that works. The RF signal is given by a sinusoid with the frequency omega RF, and the LO signal is given by some sinusoid with the frequency omega LO. When we multiply these to find IF, we can use the angle addition formula to convert the result from a product of sinusoids to a sum of sinusoids. We get one signal at an output frequency of omega RF plus omega LO, and one signal output at omega RF minus omega LO. So a higher and a lower frequency than the input frequency. Here's a graphical version of that same conversion process. The mixer multiplies the RF and LO signals in the time domain, which means that it convolves them in the frequency domain. That means we get 2 copies of the RF signal, one centered on omega LO and one centered on the negative omega LO. This results in a copy of our signal close to DC for the RF and LO values that we've chosen. So we've effectively taken the high frequency sinusoid we had at omega RF and made it into a low frequency sinusoid at omega LO minus omega RF. The term intermediate frequency refers to any frequency that's lower than RF, but there's a special term for bringing your signal down very close to DC, and that's referred to as direct down conversion. So this whole process is down conversion, and specifically direct down conversion. The down conversion process from the previous page is replicated here with some additional annotation. The signals in the middle are highlighted as the desired signal, which is the low frequency copy of the high frequency input, the high frequency RF input. But this very high frequency signal that we have at omega LO plus omega RF is labeled as the image signal. Images are generally undesirable, and they in particular because they can pose challenges for sampling. They can get aliased down into your desired signal if your sampling rate is, say, somewhere down here. As a result, mixers are often followed by a low-pass or a band-pass filters that are called image reject filters, which are supposed to get rid of images. The bottom half of this slide illustrates using a mixer in the opposite way for up conversion. Again, we start with a low frequency signal in the time domain, we convolve it with a local oscillator, and we wind up with 2 copies of the low frequency signal at omega LO plus omega IF and omega LO minus omega IF. Up-converted signals don't have images per se. We might care about both of these copies, since they are both our input signal. But we do have 2 sinusoids in our output spectrum where we only had 1 at the beginning, so it's a little bit frequency inefficient. Some very clever transmitters called single sideband transmitters can cancel out either the higher or lower sinusoid before it's transmitted, resulting in only 1 set of spikes at the output. Alternatively, one of the features of direct down conversion mixers is that they make use of both of these spikes, because both of them will get shifted back to DC where they'll add up constructively. There are lots of ways to build mixers, but I want to draw your attention to one big category that splits mixers into 2 camps. One, which is the split between passive and active mixers. One type of mixer is called a passive mixer, and it works by controlling switches to flip an input signal upside down. These mixers don't require external power, and they often have very good linearity and noise performance. The other type of mixer is an active mixer. It works by adjusting the gain of an amplifier with the LO signal. This type of mixer has bigger output signals, but often worse design complexity, linearity, and noise. These blanket statements don't necessarily apply to any specific mixer. Be sure to do your research before you settle on one for a design. I just wanted to make sure you knew that both types existed, and active mixers are going to require power supplies and perform slightly differently. So in summary, mixers convert signal frequencies by multiplying two signals together, and this has the effect of creating two outputs, one at the sum of their frequencies, of the LO and RF frequencies in this case, and one at the difference of their frequencies. IF stands for intermediate frequency, RF stands for radio frequency, and LO stands for local oscillator. When you're down converting with a mixer, you get an undesired output called an image that you have to pay attention to, and mixers come in passive and active varieties.